Okay, so let us start this new lesson in number theory. This is probably the most important part of the topic of number theory, and it is called modular arithmetic. So let me start with the concrete definition. Okay, so I want to define something for you here. So definition. So I would say let A and B be integers, and let m greater than 1 be a natural number. A natural number. Okay, we say that A is congruent to B modulo m, and write, this is the notation we use, A congruent is this sign by B modulo m, you put it on top, and write this if m divides A minus B. Okay? So the words that I am defining here is the congruent and modulo, yes. So what I'm telling you in definition, I am telling you whenever you see this in a math text, what is the meaning of this symbol? That's as simple as that. I am telling you this is true if the number on the left minus the number on the right becomes a number which is divisible by the number on the top. Okay? Before forgetting about this, in other math textbooks and even in your book, this is slightly written differently. So let me write it here. So this is the way that your book has written it down. So in your book, you see this symbol. Oh, sorry, this is my symbol. And then the book you have write mod for modulo, m here in pairs of brackets. I don't know why this notation has survived. You see even in math books like this, because it actually, if you are a mathematician, you try to be lazy as much as you can, yes? So why should I write so much time if I can have a compact notation like that? But in your book, if you see this, this is the same as what I have written there. And I will use my own notation because it is simpler to write. Okay, so this is one thing. So this is in the book. This is the notation that you use in the book. Okay. So let me give you some examples. So this seems a little bit artificial unless we give some examples. For example, number 1, I can write 15, for example, is congruent to, say, 3 modulo 4. If you don't mind, let me... So I am telling that 15 is congruent to 3 modulo 4. Why? Since the number on the right minus the number on the left, the number on the left minus the number on the right is divisible by the number on top. Is it true or false? 15 minus 3 is 12. 12 is divisible by 4, so it's a true statement. If this is true statement, this is also true. Okay, so checking this if this is true or false is extremely simple. Okay, another thing, for example, I can take the same 15, I can take the same module, but let me change it to minus 1. Do you think that this is true or not? Again, it's also true. Why? Since if I take the number on the left minus the number on the right, which is minus 1, it becomes a number, which number? 16, which is divisible again by 4. So it is true, so that's also true. Okay? I don't know, for example, number 3. So I don't have any batteries here. So let's just get rid of it. Okay. So here, let me give you another example. So for example, let us write minus 42, and I would write it as congruent to 7, and I would write here 14. Do you think that this is true? Let us check. If I want to see if this is true or false, I need to take the number on the left minus the number on the right, and then ask myself, is this number that I generated in this way divisible by the number on top or not? If the answer is yes, this is true. If the answer is no, this is false. So in this case, minus 14 minus 42 is minus 56. Minus 56 is divisible by 7. Yes? So this is true. So we say this is, since this is true. Or I don't know, for example, number 4, if I have 7, and then I would write here, for example, minus 1, and then I would write 3 here. Is this true or false? True. Then the number on the left minus the number on the right becomes 8. Yes, can you see that? 7 minus 1 is 8. 8 is not divisible by 3. So that is false. So, but I take this one off. So this is true again. Since 7 minus 1 is not divisible by 3. So it is very simple. But the power of this modular arithmetic is, look here, 15, for example, is congruent to 3 modulo 4. It is also, for example, congruent to minus 1 with the same module. Okay? So this is the power of this kind of arithmetic. Of course, when I say power, it doesn't mean that you can destroy China by it, but I mean the power of it within mathematics itself. Okay? So here, if you see I have 15, if I want to stick to equality relation, 15 and 3 are not equal, 15 and minus 1 are not equal. Equality is very limiting relation. So they have to be exactly equal to call them equal. But congruency is a little bit looser, yes? So it means that, for example, I can have different names for the same number if I take the lens of congruency. Okay? So this is a very good idea to think in that way. 3 and minus 1, you need to imagine it, they are different names of number 15 if you decide to work in this module 4. Okay? Is that clear? So this is a good idea to have this feeling that when I write congruency, I am giving different names of the same number, but if my lens is the lens of congruency. Okay? So for example, can you give me another name for 15 if I decide to work in congruency in module 4? So 3 is one name of 15. Why? Because this is true. Minus 1 is another name for 15 because this is also true. Can you give me another name for 15? Yes? 7. Let us check. So you are saying that 7 is another name. So it means that 15 should be congruent to 7 module 4. Is this true or false? Everyone should be immediately saying that this is true or false. Is it? Yes, because this one, left one, minus the right one is 8, and 8 is divisible by 4. Yes, you are right. So 7 is also another name for 15. Yes? So another question, how many names do you think I can present for 15? Yes? Infinitely many. Yes? Do you agree with me? So let us see why. For example, 15, I want to see how many names, I don't know this yet, I want to see how many names I can write for 15. Let us say I write n. What is the meaning of this sentence? The meaning of this sentence is that, the meaning of this statement, in mathematics we say statement, the meaning of this statement is that the number on the left minus the number on the right is divisible by 4. Yes? But what is the meaning of this? We had the meaning of divisibility before, because I am looking for all names of n. So I would say that when you say this number is divisible by 4, what does it mean? It means the right-hand side is an integer multiple of the left-hand side. It is 4 times q. Yes? And then there exists a q in z. Is that understandable? This is the meaning of this sentence. And then what does this mean? This means that if I am looking for n, so n becomes 15 minus 4q. Yes? Q is an integer. So this is all possible numbers that are congruent to 15 modulo 4. Yes? For example, if I choose q to be 0, sorry, if I choose q to be 0, it is 15. So yes, 15 is another name for 15, which is trivial. If I choose q to be 1, for example, it generates for me 11. Yes? So 11 is also another name for 15. Yes? Because 15 minus 11 is 4, and 4 is divisible by 4. So by assigning different integer values to q, you generate all possible names of 15 if you have decided to work modulo 4. Yes? Is that right? This is a good thing to remember. So when we are dealing with modular arithmetic, every number in a given module have infinitely many names. Yes? Okay. But now, why this is good? Because the properties of modular arithmetic is very similar. The properties of this new relation is very similar to the properties of equality sign. And because we already know how to work with equality signs very good, in principle, we can use that knowledge and start working with this very effectively. Let me tell you something. Let me tell you how. For example, one of the main important properties of equality sign is what? Every number is equal to itself. Yes? Every number is equal to itself. Yes? Exactly the same thing happens in congruency. Every number is congruent to itself in any module that you like. Yes? By the way, why do you think I excluded 1 from being a module? Yes?
Because anything divided by itself is 1. No, anything divided by 1 is itself.
Okay, but so why we should exclude? Is this a problem? So my question is that you see that I told you that module should be greater than 1. In principle, I could also allow for m being 1. Why do you think I excluded 1? Because 1 is not an interesting thing, yes? Because if m is 1, as you are trying to say probably, a minus b is automatically divisible by 1. So if I decide to work in module 1, every number is congruent to every other number modulo 1. Yes? So that is not something interesting. So this is why we exclude 1 from the being module. So we know that a is equal to a. I am saying that any number is also congruent to the number itself when it comes to any module n. Why this is true? Do you agree that this is true? Yes or no? It is true, yes? How do you check this is true? You need to ask yourself, is it the case the number on the left minus the number on the right is divisible by the number on top? Is this a statement true or false? If this is true, then this has to be true. And if it is false, then this is false. Which one is that? M divides a minus a. Is it true or false? So what is this number? 0 is divisible by m. Is that right or wrong? Yes or no? Yes, it is true. Yes. So this is also true. Okay. So any number is congruent to itself when it comes to any module. Another important property of equality sign is that if A is equal to B, then B is also equal to A. Yes? Do you think this is also the case? If someone grants you this, do you think if you want, you are allowed to conclude the other way around as well? If I tell you this is true, do you think you can conclude this one is also true? Exactly like we had. If I tell you this is true, do you think this is true or not? Let us say I grant that this is true. Then you immediately realize, okay, if this is true, this is also true. Yes? Is it the same thing for this kind of relation or not? Yes or no?
Yes.
Why? Because when you say this is true, what does it mean? It means A minus B is divisible by M. But you know that if A minus B is divisible by M, can I say B minus A is also divisible by M? Yes or no? Because B minus A and A minus B are essentially the same numbers, the only difference is the sign. If this number is divisible by M, negative of that number is also divisible by M. So if this is true, then this is also automatically true. Yes? So far, these two relations can translate themselves into this new language. So another property of equality sign is that if A is equal to B and, this symbol means and, B is equal to C, what can I conclude? A is equal to B, B is equal to C. Then A is equal to C. Okay? This is called reflexivity. This is called symmetry. This is called transitivity. You don't need to know the names, but in case you are interested. So far, this relation is also reflexive. This relation is also symmetric. I want to ask you, do you think this is also transitive? In other words, if I grant you these two and this, do you think you are allowed to say similar thing that you said for equality here as well? In other words, do you say that this is also true? Let us say this is true, this is true. Do you think that this is also true? Yes or no? This is in the book, the proof is in the book, so let us just do it for you. So you say that A is congruent to B modulo M. What is the meaning of this? The meaning of this is that the number on the left minus the number on the right is divisible by M. Yes? You also tell me that B is congruent to C modulo M. So I am allowed to conclude what? The number on the left minus the number on the right is divisible by M. Yes? But now from here, do you remember what is the meaning of this? It means the right-hand side, it means there exists a Q where in Z such that the number on the right is equal to the number on the left multiplied by that Q. Yes? If I translate this, again, this means there exists a Q, but I have to change the letter, so let me write a Q prime in Z such that what happens, B minus C is equal to MQ prime. Yes? So if I tell you this is true, you are allowed to write all of them because you are following the definitions. Okay? But now, if I start adding them up, what happens side by side? This number is equal to that. This number is equal to that. So it is clear that if I add this number and that number, it becomes equal to if I add these two numbers. Do you agree with me or not? Yes? Okay, but what happens now? This minus B and B are gone. Then I am left with A minus C. On the right-hand side, I can factor M out. It becomes Q plus Q prime. Okay? And then Q and Q prime are integers, so when I add them, it becomes another integer. Okay, so what happens now? A minus C is M times capital Q, and capital Q is an integer. So what is the meaning of this? This means that this number is a multiple of m, an integer multiple of m. So it means a minus c is divisible by m. Yes? But a minus c divisible by m means what? Means a is congruent to c modulo m. Yes? Understandable or not? Yes? Okay. So you see, this is the good thing. You don't need to memorize them. We have to convince them. We have to convince ourselves that this is indeed true. But after we are convinced, we don't need even to remember it, because it's exactly the same thing that we have for equality. It's already in our head. Okay, so now this is done. Let us go to the other scenarios here. So these are the three fundamental things that I want you to know. Okay, let us see that what else we had for equality signs. So for example, if I give you A equals to B, do you think I can conclude, if I say this is true, do you also believe in me that this is also true or not? Yes, if I tell you that this is true and C is any number, do you agree that this is also true? Yes, because I am adding the same amount to both sides. If they are equal, after the same amount is being added to them, the results will be the same. Okay, and now the question is that, do we have some property like this when it comes here? And the answer is fortunately yes. So if A is congruent to B modulo M, and if C is any number that you like, you can add C to this, add C to this, and still they remain congruent. If this is true, this is granted to be true as well. Okay, what about this one? Can I subtract here? If A, yes, if A is equal to B, A minus C is also equal to B minus C. The same thing will happen here as well. Okay, can I multiply by C here?
Yes.
Yes, the same thing happens here as well. So if A, B, and then this A times C, of course I am just telling you accept them. The proof are easy. I prove the hard one later. Here, equality sign, I want to warn you about that. In equality sign, division is also correct if C is not 0. Okay? So if A is equal to B and C is not 0, if I divide A by C and B by C, still they are the same. But this is gone there. Why? Because if you divide two numbers, there is no guarantee that I have an integer. And this symbol only makes sense if the left and right sides are integers. Otherwise, it doesn't make sense. I cannot talk about 1 over 2 is congruent to 3 over 5 modulo, I don't know, 5. This is meaningless at all. Yes? So I have to have integers on both sides. So this is for this reason that even though for equality we have this, but for congruency we don't have division. So remember, that is one of the remarks that you have to remember. Okay? So let me write the properties 1, 2, 3, and 4, and 5. Okay, let us go more. What happens here? If I give you A is congruent to B, modulo M. Sorry, let me do it for equality first. If A is equal to B, I also tell you C is equal to D. Do you think I can say A plus C is equal to B plus D? Is it true or false? If I grant these two, can you conclude this one if you want to? Yes, you can add them side by side. Subtraction is also valid. Multiplication is also valid, yes? Yes? Okay, so if these are true, you can conclude both of them. Are they the same? So in the case of congruency, we also have this, fortunately. So if I have this one, congruent to B modulo M, and if I have this one, modulo M, you can conclude all of them if you want to. You can conclude that A plus or minus C is congruent to B plus or minus D modulo M. You can also conclude that A times C is congruent to B times D modulo M. But again, here the division is also allowed if they are not 0. Yes? But there division is not allowed for the same reason that I told you before. So addition, multiplication, and subtraction are quite good, but when it comes to that, we don't have it. So this is property number 5. So this is property number 6 and 7 if you want to, but let me just write 6. Okay, I want to prove this one. The proof of this one is in the book. So I have only just told you, trust me on that, because the proofs are simple. But the proof of this one might be a little bit complicated. I want to convince you that if you tell me these two are true, I am allowed to conclude that this one is also true. But how do you think I will do that? Because you need to learn this one as well. So these are my assumptions. I can use them. And this is what I want to show. Okay. You are telling me that A is congruent to B, so I can use it. How should I use it? There is only one way I can use it, and that is the definition of that. What is the meaning of this? The meaning of this is that the number on the left minus the number on the right is divisible by the number on top. And when you tell me that C is congruent to D modulo M, I can conclude the same thing. The number on the left minus the number on the right is divisible by M. Yes? But what is the meaning of this statement? The meaning of this statement is that there exists a Q in Z such that the number on the right is equal to the number on the left times Q. But what can I write here? I can move B to the other side and write this. Yes? Yes, so the algebra is very simple. The same thing here. So there exists a Q prime in Z such that the number on the right, C minus D, is equal to this number times Q prime. And then I move D to the other side. So C becomes equal to MQ prime plus D. And of course, Q prime also belongs to Z. Yes? Okay, what I want to do now, I want to know something about AC and BD. Okay, so this might motivate you to multiply them side by side because you need to know something about AC. And the only information that I have in my hand is this one and that one. So I have to use it in some way. So the most natural way to use it is probably to multiply them because you need them, yes? So therefore, A times C is what? A is equal to this, C is equal to this. So if I want to multiply A and C, instead of A, I can write the number equal to A. And instead of C, I can write the number equal to C. Yes? And then what happens? You can open up this. MQ times MQ prime is M squared QQ prime. And then this one, that one is MQD. This one with that one is MBQ prime. And this one with that one is B times D. So let me write this. Yes? And now what happens? This is the good thing because I also needed BD and BD appeared. So that is good. But what can I do with this mess? Any ideas? Pardon? Factor M. Yes, because you have enough experience, hopefully. Yes? AC becomes, I can factor M out. I am left with MQQ prime here. I am left with QD here. I am left with BQ prime there. And then I had a BD at the very end. But can I make sure that this is actually an integer? Yes, because M is a natural number, Q and Q prime are integers, B and D are integers, so this combination definitely is an integer. So I can call it capital Q, which I am sure is an integer. So let me write it here. Now I move BD to the left. There is a reason I'm doing that. So AC minus BD is M times Q. but q is an integer. Okay, so let us see that what can you conclude from this one. AC minus BD is n times q, where q is an integer. Everyone, what can I conclude from this one? Everyone, please, what can I do that?
AC is congruent.
Not you are going 2 steps ahead, but 1 step. What can I conclude from here? Yes?
AC minus BD is divisible by
M, or in this notation, M divides AC minus B. Yes? And then what is the translation of this into this new language? This is playing the role of the number on the left. This is playing the role of the number on the right. And this is playing the role of your module. Yes? So this means that AC is congruent to BD module M. So this is one of the problems in the book. Okay? So if A is congruent to B and C is congruent to D, then A times C, so you can multiply them side by side, you can add them side by side, you can subtract them side by side, all of them remain valid. Yes? Okay, do you remember something else for equality sign? If you remember, we could raise to some powers, yes? For example, if I have A equals to B, can I conclude that A to power 2 is equal to B to power 2? If I say A and B are equal. The other way around might be problematic, but in this direction, that's okay. Can I say A to the power of 3 is equal to B to the power of 3? Again, yes. Okay, but I can write A to power n to the power of n. So this is one of the properties of equalities. That property is also can be transferred into this new relation. So I would say that if A is congruent to B modulo m, then A to the power of n is congruent to B to the power of n modulo m. But here I have to have n a natural number. In this case, n can be any number. But in this case, for example, n cannot be negative because a to the power of minus 3 is 1 over a to the power 3. It will no longer be an integer. So it has to be a positive number. But this one can be any number. So if you have this relation, you can raise this side and that side to any natural power that you desire. Why is that? Because if you tell me that A is congruent to B, I can write it once more, and then I learned that if I have two congruencies, I can multiply them side by side, it remains valid. If you tell me A is congruent to B modulo m, I write it again, because if you say this is true, this one is the same thing, that's also true, then I am allowed to multiply them side by side. But this one becomes a squared is b squared n. Yes? So I was able to show that if a is congruent to b, a squared is also congruent to b squared. What about a cubed and b cubed? Do you think a cubed and b cubed are also congruent? Why is that? Because now, when you generated this one, you consider this a new one, and you have this one, and then you multiply them side by side. This time it becomes a cubed, and this one becomes b cubed. Now that you have b cubed, you can go to the fourth power. Yes? So you can go to powers one by one. We will study this method that's called mathematical induction. That's the last part of this chapter. But anyway, I hope that you understand that if I have equality, I can immediately write this. But let me tell you that division and taking roots are not in general allowed. Even if you have integers. For example, if I have 12, let me see. If I write 4, 8. Yes, is this true or false? Yes, 12, the number on the left minus the number on the right is 8, and 8 is divisible by the number on the top, so it's true. But let me divide this one and that one by 4, because this is divisible by 4, that's also divisible by 4. If I divide that, it becomes what? 3, If I divide this by 4, it becomes 1. And now, is this true or false? This is false because 3 is not congruent to 1 modulo 8. So it was true, but this is false. So be careful. You are not allowed to divide. You are allowed to multiply, but you're not allowed to divide, because when you divide, might be you get the wrong answer. Okay? That is not possible. And taking square roots or roots is also not allowed. Okay? Any questions so far? No? Okay. So one more thing, and then we start doing. So let me start with a practical example. Might be you don't understand what's going on exactly until you see an example. But what I want you to say, even if you didn't understand the proofs and things like that, I want you to understand the content. Yes? Did you understand what I said? I said that the relations that you expected for equality, you can also expect them more or less, all of them, for this congruency relation. Okay? And now, for example, this example that I want to mention is probably a very important example that I want you to understand this part. So, let me see. Just, yeah, the chances of me asking you to prove a theorem is not that high, okay? But this example I want you to learn. So simplify the number, simplify 5. Let me use this symbol for multiplication. 5 times 64 to the power of, let us say 100. And then plus 15 times 17. Simplify this number that you see in modulo 7. Okay? So these type of questions you can see a lot in the book. So you are supposed, usually a huge number is given to you and calculator is not allowed. Okay, and calculators, by the way, is not capable of doing that much. I will tell you how to do it in GeoGebra later. But here, you have a huge number. You want to simplify it in a given module without calculator. That's the whole point. Okay. In other words, I want you to tell me other name for this number. If I want to work modulo 7, a very tangible and simple number. Okay. Okay, so how should I do that? Let me do it once in a very precise way, then I will teach you how to do it faster, which would be enough for the exam. Okay, so if I want to do it, try to just follow what I'm saying, okay? So, first of all, do you agree with what I write here or not? Do you agree with this statement? Okay, this 64 this is the number that you see here. Do you agree this is true? Yes, because the number on the left minus the number on the right is 63, and 63 is divisible by 7. So this is a true statement. Now, do you agree with me that I can write something like this? Just tell me why, okay? Yes? Do you agree with that one? Why? Because I just told you that if you have congruency, if you want to, you can raise both sides to any power that you like. It remains valid. Okay? And then, do you agree with this one as well? Yes? Why? Because another name for 1 to power 100 is just simply 1. Okay, but I just want you to understand you did a very good job here, yes? Because if I ask you, this huge number minus 1 is divisible by 7, it was not that immediate, okay? Because that's a very huge number. But that was not huge, you could do it in your head, and because you could do this in your head, you can raise it to power 100, and now you are certain about that this huge number, minus 1, becomes a number which is definitely divisible by 7. Okay, so that is the power of this modular arithmetic. Okay, but that is not the whole story, because I want to construct this expression. I succeeded to construct this and make it a very small number, 1. And let us continue. What do you think I will do? I want to construct this, so it motivates me to have this and multiply it by 5. So I multiplied by 5. Am I allowed to multiply both sides by 5? Yes, because we just discussed about that. Yes, it is still on the board. If I have this, I can multiply it by any number that I like. I decided to multiply by 5. Why? Because I see a product of 5 here. So this becomes 5 times 1, and then I have 7. But of course, 5 times 1 is simply 5. Yes? So here you can keep it. So it is very important to understand that if you are supposed to work in module 7, this number has a simpler name, and that is simply 5. Okay? Okay. Now what about this one? So what can I write for 15? Can you give me a better name for 15 if I decide to work modulo 7? Of course, I told you there are infinitely many names for any number, but give me one good number. Yes? 1. Do you agree? Because 15 minus 1 is 14. 14 is divisible by 7, so 15 is 1. Can you do the same thing for me for 17? Give me a number, give me another name for 17 modulo 7. 3, yes? Because 17 minus 3 is 14. 14 is divisible by 17, by 7. Yes? Now, do you think I can write this 15 times 17 is congruent to 1 times 3? Am I allowed to do this? Yes? Which property? This property. If I have two congruencies in the same module, if I want to, I can multiply the left-hand sides, I can multiply the right-hand sides, and I am sure that this is true again. Okay? So you are certain about this, you checked it manually by hand, you are certain about this, you checked it, and according to this theorem, I can multiply them side by side, and according to that theorem, this remains valid. Okay, but what is this number simply? Is just 3. So you see, when you decide to work modulo 7, this number is not a huge number, but 3 is better than that, yes? But 3 is another name for that number. Okay, now let me call this one number 1, let me call this one number 2. I want to have this construct. So it motivates me to add them, yes? Am I allowed to add them? So am I allowed to, from 1 added to 2, I can conclude that this number plus this number, yes, is congruent to this number plus that number modulo 7. Okay? Am I allowed to do this? Because of what? Again here. If I have two congruencies, if you need, you can add them side by side, it remains valid. Okay? But now, there is another name for 5 plus 3, so what is that? You can write 8. You can write equal 8 or congruent to 8, because every number is congruent to itself. So that's it. So if I ask you, or if you work in module 7, 8 is another name for this huge number. 8. But can I find even a better name? What? 1. 8 is 1. Yes, understandable. Because 8 is congruent to 1 modulo 7. Why? Because 8 minus 1 is 7. 7 is divisible by 7. Yes? So what I realized that is this number is of course completely different from 1. But if you care working in module 7, this number has a very simple name, and the name is 1. It has infinitely many names, but one of the names is this simple number 1. Is that clear? Yes or no? Okay. So this is what I want you to learn. So this is a very long way of doing that. Okay, so now that you learned, so I did it in this way because I wanted to show you that I didn't waste my time. Because everything that I told you here somehow was used when I was solving that problem. Okay, now that you understand that that was not a waste of time, we can do it faster. Okay, let me just do it faster for you. And this is what I want you to learn. Okay, because when I teach, I want to teach you in a way that you understand why this is working, and then we just, after we learn it is working, we just do it fast. So if I want to do it myself, what do I do? So I start right like this. Any number that I see in the base, so you see that if you have a to power n, this is called a power. This number is called exponent, and this number called the base. Yes? So whenever you want to simplify something in some module, usually this is the case. You have very big power, very big exponents involved. Okay, but you need to know the bases. These numbers are appearing in the bases. The exponents here are 1, the exponent here is 1, the exponent here is 10. You can simplify the bases only in that module. Okay? Okay, should I simplify 5? 5 is a fairly small number, so I don't make trouble for myself. 5 is good. Okay? So I keep it. But 64 is a number above my module. You see, 5 was already below my module. But 64 is above my module. Any number in the base which is above your module, it is better to be simplified as much as possible so that you can do it with your head. For example, then you need to, this is the creative part, so you need to, a little good. So you need to give me another name only of 64. Forget about the exponent. What about 64? What is a good name for 64 when it comes to module 7? It means that, can you tell me a number so that 64 minus that number is divisible by 7? This you need to train your brain for, okay? If I ask you, give me another name for 64, module 7, I am asking you, can you give me a number so that this 64 minus that number is divisible by 7? So you need to ask this question. And of course, if you practice, you can answer this quickly. So what is that? 1. So you replace this with 1. Okay? And then you have the exponent there. You have to copy and paste the exponent. You are not allowed to touch the exponents. You are only allowed to touch the bases. Okay, and then I go forward. I have plus sign. Do I have a better name for 15 when it goes to module 7? Yes, what is that? 1. So just replace it and write 1. And then after that, multiplication. Do I have another name for 17 in module 7 which is better?
Yes.
What is that? 3. Yes? And module 7. And then do the calculations. 1 to power 100 is 1. Times 5 is 5. This is 3, so it becomes 8. Yes? So that is just one line. You don't need to write all those things, okay? But if this is okay with you, you can stop. If it is not okay, you can simplify more. Usually, when you have a number which is above your module, it is better to simplify it to a number smaller than the module. So I do not stop here usually. I continue and write what? 1, 7. So this is what I want you to do, okay? So, and all the things that I told you there, in this case, it is not clear I am using them. But when I did them, this is the way that the book does it, okay? But you don't need to do it so long, so you just do it quickly, like that, okay? But now you understand that all those theorems are essentially needed when I was doing it. Any questions? When the lesson ends, do you know?
30.
30. So we have a little bit of time to say that what happens now. This is the important remark. This is also a very important topic for the exam, okay? Let us say that a is an integer let us say that m is a natural number. Of course, to be module, m should be also greater than 1. So let us assume that this is the case. So, and somehow you understood that a is congruent to r modulo m. Okay? So I give you a number, a, I give you a number, m for the module, and by investigation, you realize this number given to you has another name r when you are working a module. And this number is less than the module, but greater than or equal to 0. Okay? If these two conditions are met, from these two conditions, you can conclude that R is the remainder of A by M. Okay? So this is probably the most important thing in modular arithmetic that you need to know. Okay? So if A is congruent to R, in other words, R is another name for A, but that name is less than the module and greater than or at least equal to 0, then this number that you see here is the remainder if I divide A by M. Okay, I will say why first. For example, instead of asking you to simplify this expression, the book usually don't ask you to simplify. They ask you like this: find the remainder of this number if you divide it by 7. Yes, this is the way that they ask the question. So, what is the remainder if I divide this huge number by 7? Okay, can you answer that now? It's 1. Why? Because we simplify that number, and I realize this number is 1 when I work in module 7. On the other hand, this number 1 is less than my module, and it is non-negative. So this number is what? Is the remainder. Yes? Of division of this number by 7. Can I say 8 is the remainder because 8 also appears here? It is not wrong to say this is congruent to 8, but 8 cannot be a remainder because the remainder should be less than my module. 8 does not have that property. Yes? For example, instead of 8 is congruent to minus 6 modulo 7. Do you agree? Because 8 minus 6 is 14. 14 is divisible by 7. So if I write minus 6, that is not wrong, but minus 6 cannot be used as the remainder because the remainder should be non-negative. So whenever you have a number which is congruent to another number and that number satisfies those conditions, then you can immediately make sure that this number is the remainder of A by M. Yes? And why is that? The reason is simple. Because when you say A is congruent to R modulo M, it means that M divides the number on the left minus the number on the right. This means that there exists a Q in Z such that A minus R is MQ. Then it means that A is equal to MQ plus R. Do you remember the division algorithm? The division algorithm told you that if you have something like this, and this R is greater than or equal to 0 and less than the absolute value of M, which in this case is M because M is positive, then this is the remainder. Okay, this is the proof for this remark. Okay, but if you don't like proofs, you can just use it. Okay. So this is, you will see a lot of these questions in the book. For example, find the remainder, find the first digit number. We will come to these kind of things. Okay? Any questions? Okay, thank you very much. Just wait a little bit so that I can stop it.